Hello everyone, I'm Yong from Nanjing Tech University, China. My presentation is one of the role of tendons for fire safety design of pretensioned steel structures. My presentation includes 6 parts. As well known, pretensioned steel structures includes tensile steel cable nets, beam string structures, suspension domes, suspension bridges, cable stays bridges, and so on, which always cover long span. Fire is one of accident loads that would occur during the whole service life of pretensioned steel structures. It would be noted that pretensioned steel structures are different from those frame structures. A series of characterized tendons are displayed as these pictures, including steel wire, steel strand, steel cable, current, pretensioned cable, and so on. Temperature distribution of localized fire is different from compartment fire. Both of hot smoke and fire flame would transfer heat to environment. Herein, flame radiation rule is proposed by regression formulas, which are dependent on amount of parameter analysis by using FDI software simulation. When radius of radiation spheres are determined by simple method, the radiation heat on the vertical surface is dependent on the distance from center of fire to the vertical surface. Temperature distribution on ceiling and the vertical surface also have been developed by amount of parameter analysis with FDI software. Both of regression formulas for temperature distribution are dependent on the heat release ratio, heat of ceiling, and the coordinate in building space. The geometric curtains of strings or cable with cavity between wires is different from that of steel bar. So cavity radiation should be considered suitably, corresponding to the lump competence equilibrium. An analytic solution of this temperature history of a central well in steel cables was proposed. The temperature history in the center of steel strings is most dependent on total thermal resistance of heat transfers between environment and steel cables. Thermal conduction resistance in radius of steel strings. Thermal resistance of heat transfer by radiation of cavity. The temperature deviation between two models are up to 115 degrees in 15 minutes. The analytical method fitted well with the numerical simulation using by Abacus software. Experimentals are conducted to determine the specific heat and thermal conductivity of filling materials, such as zinc copper iron for hot cast anchors, and the mixture of epoxy resin and steel shot for cold cast anchors. A formula to calculate the transient temperature distribution of fillers in hot cast anchors is derived based on the lump capacitance equilibrium, which is dependent on the thermal properties of filler material. The temperature along the central axis of anchors is non-linear, shown as picture above. The full range of stress-strain relationship at elevated temperature was captured by DIC system for the first time, as shown in figures. Fitting curves are different as clamping action on the twist wheels. The effective yield strength at 1.25% strain rather than 2.0% for twist strength is proposed. The radiation factors of the effective yield strength, proportion limit, elastic modulus, and ultimate strength for 1,860 MPa twist strength are fitted to test data well, as shown in figures, as well as 1,670 MPa parallel strength. The formula of thermal strain and expansion coefficient dependent on temperature is determined from regression analysis on the test data for twist strength and parallel strength respectively as above. A regression analysis is carried out to develop a set of new parameters as listed in table for time hardened creep model based on the test result of 1,860 MPa twist strength and 1,670 MPa parallel strength respectively. Study on the material properties dependent on temperature and temperature distribution due to localized fires in nature are given above. The thermomechanical analysis of pretensioned steel structures has been investigated as below. Firstly, a general equation of the horizontal tensile force of pretensioned steel cable has been derived from force equilibrium and deformation compatibility. A simple method has been proposed, which can be benefit for civil engineers to check the fire resistance of a single cable under distribution load or point load exposed to localized fire. Numeric analysis using ANSYS software discovered that the steel cable would fail as rupture strength achieved at elevated temperature when the high temperature creep strain was considered. It is worth noting that the ultimate strength of cables would not be achieved at elevated temperature, since the creep strain enhanced the reactions of cables. Thus, when the total strain of steel cables increased dramatically due to the increase of creep strain after 300 degrees, the tensile force decreased more greatly than ultimate strength in cables at elevated temperature. Beam string structures is a kind of self-balanced structures which contains upper rigid beam and pre-stressed cable joined by struts as shown in figure. With respect to the differential elements in the coordinate system, the static equilibrium equation of differential elements for the cable and the rigid beam subject to localized fires can be established respectively. General formulas of horizontal tension force of pretensioned steel cables, bending moment of upper rigid beam, and compressive force of struts were derived as above. A simple method also has been proposed to check the fire resistance of BSI structures exposed to localized fires. A suspension dome is formed by the upper single-layer dome and the lower pretension cable strut system. The pretensioned ring cables enhance the stiffness of group structures. For advanced method, it is worth noting that, as a group of suspension dome subject to the age-localized fire, the non-uniform temperature distribution along the pretensioned ring cable is unbalanced due to different thermal expansion. Then, when the resultant force overcomes the friction between the surface of the cable and the clamping node, the cable would be slipping and the pretensile force is redistributed just like an elastic band. Slipping action can be discovered by the displacement histories of ring cable elements as each node, as figure above. In order to simulate the slipping dependent on slipping resistance by using ANSYS software, the combined 40 element was simplified to simulate the joint between a cable and the lower end of the strut. For design procedure of structure fire safety, this study provides key skills and integrated the flowchart step by step. First, temperature distribution fulfills the fire temperature and the temperature distribution of elements. Second, properties of steel strength at high temperature contribute on material properties at elevated temperature. Third, thermomechanical actions of pretensioned structures helps to estimate the structure response under localized fire. That's all. Thanks for your attention.